Hello everyone, and welcome to Recitation with Sohail. Today we're going to do problem 32 from section 6 of chapter 3 of the 10th edition of Boyce and DiPrima. So we want to solve the differential equation given to us in equation 1, namely that 1 minus t times y prime prime plus t times y prime minus y equals 2 times t minus 1 squared times e to the negative t, and we're solving it on the interval t between 0 and 1. And as you may notice, while this is a second order linear differential equation, and it's non-homogeneous, and it's not super basic, it's not an Euler equation, or it's not a constant coefficient differential equation, so it's not something where we immediately know how to jump into it and start finding the solution. However, we can use the method of reduction of order, which is what we're going to do, because they did give us one of the solutions. We are told that y1 of t equals e to the t is a solution to equation 1. And if we are magically given such a solution, then we can, y1 of t equals e to the t is a solution to the corresponding homogeneous equation, which means that this term here is replaced by 0. Then e to the t is going to be a solution. And if by some magic we're able to obtain such a solution, then we can use the method of reduction of order to reduce this second order linear non-homogeneous differential equation into a first order linear non-homogeneous differential equation, and then we can just solve that using a standard method like a integrating factor. So that's what we're going to do. For the method of reduction of order, we assume that our second solution is a multiple of the solution we are given to the corresponding homogeneous equation. So we assume that there is some function v of t such that y of t equals v of t times y1 of t, which happens to be the same as e to the t times v of t. Now, we'll see why this is a useful guess later on. But for now, in order to get a differential equation in v, which is the new function we want to find, because once we find v, we will have found y, we need to go ahead and, calculate y prime and y prime prime in terms of e to the t and v of t, so that we can go ahead and substitute it into our equation and get a new differential equation. So we go ahead and just do that by direct calculation. Equation 2 is a simple application of the product rule to y of t. Here I took a derivative of the first term, so derivative of e to the t is still e to the t. Second term is unchanged. I add to that the first term, e to the t, times the derivative of the second term, v prime of t. Then for y prime prime, I do the same thing. I now have to use the product rule twice. Conveniently, this first term, e to the t times v of t, is exactly the same as what we saw before. So when I take a derivative of that, I'm just going to generate another copy of this. I'm going to get another e to the t times v of t plus 1 e to the t times v prime of t. Then when I add the derivative of the second term, I have to use my product rule, so derivative of e to the t is just e to the t. That's what gives us the second term. And then I add to that the first term times the derivative of the second term, which is where e to the t times v prime prime comes from. So now that we have expressions for y of t, y prime of t, and y prime prime of t, we can go ahead and just substitute those into our differential equation. So we're going to go ahead and do that. we can see that here is our y of t, which I'll plug into there to get this. Then we also have our y prime of t is equal to all of this, which I will plug into here to give me everything in between these two parentheses. And lastly, y prime prime of t is equal to all of this. So I will plug that in here to give me everything in between these two parentheses. So far, all I've done is we assume that the solution y of t is of the special form e to the t times v of t. We calculated y prime, prime. We directly plugged those in to the differential equation that we were given. Equation 4 is the same as equation 1 that we were given. I just switched the left and right hand sides. Now, this is where we're about to see the magic of reduction of order. So I'm going to regroup these terms. I'm going to gather like terms. Namely, I'm going to gather all of the v of t's together, the v prime of t's together, and the v prime prime t's together. So here's my v of t's, and I will gather all of those terms together. So e to the t times 1 minus t gives me that. T times e to the t gives me that. Negative e to the t gives me that. Then all of my v prime of t terms, I will gather those together as well. So those two come here. 2e to the t times the 1 minus t on the outside, it gives me this term. Then t e to the t gives me this term. And lastly, there's only one v prime prime of t, so I will go ahead and collect that as well. Unfortunately, it looks like I did forget to write the 1 minus t over here, so I apologize for that. But thankfully, it does show up later on. We can see that it is down there, so I did account for it later. But now, here's the magic. Now that we've regathered the terms together, we see that here 1 times e to the t minus e to the t, those cancel out. Negative t e to the t plus t e to the t cancel out. So all of this turns out to be 0. Right? That is 0. So 0 times v of t, the v of t goes away. And that's the magic of reduction of order. This will always happen when you use the method of reduction of order, because this e to the t that we started with, or to be more precise, this e to the t over here next to the v of t, because we assume that was a solution to the corresponding homogeneous equation, this part, the coefficient of v of t after we plug everything in, will be 0. So because v of t is gone, we can also just simplify the rest of the algebra here. The conclusion is that 2 times t minus 1 squared times e to the negative t, so this is equal to this. And now this looks like a second order differential equation, but we're going to see shortly that it's really a first order differential equation if we look at it as a differential equation for the function v prime instead of the function v prime prime. But before I work that out in detail, just what we normally like to do when we're working with linear differential equations, which regardless of whether we make a substitution for v prime or not, the gray equation that's the result of our calculations is still going to be a linear differential equation. We like to have our leading term have a coefficient of 1. It normalizes the differential equation. So I'm first going to divide by this 1 minus t times e to the t, which also just a small note. E to the t is never 0, so we can always divide by that. And 1 minus t, we can divide by that because we're assuming that t is between 0 and 1, so 1 minus t is not 0. So that being said, we go ahead and do the division, and we see that the result is v prime prime of t plus 2 minus t over 1 minus t times v prime of t equals 2 times 1 minus t times e to the negative 2t. And now we see that equation A is a normalized first order linear differential equation with respect to the function v prime of t. Right, here's a function v prime, and v prime prime is just the derivative of v prime. So I will solve for v prime by using an integrating factor, and then afterwards I'll just integrate it to get v, and then we can plug it back in to get our the answer to the original equation. And I'll go a bit fast on this part. I'm assuming once you're in chapter 3, you guys are all comfortable with integrating factors. So the integrating factor, we just use the formula e to the integral of p of t dt, where p of t is here the coefficient of the v prime of the term that's not being differentiated, so to say. And again, this formula for integrating factor works because we normalize the differential equation. Because the coefficient, the leading coefficient here is 1, I can go ahead and apply this formula for integrating factor. So now I'll just plug in p of t is just 2 minus t over 1 minus t. I will rewrite this in a slightly more convenient form in order to perform the integration. I will note that 2 minus t over 1 minus t is 1 over 1 minus t plus 1. Now, pretty easy to integrate. I see that the first term integrates to negative natural log of t, and the second term integrates to just t. And I put the little stars on the equation because normally an indefinite integral has a constant of integration. I chose that constant to be 0 for convenience, as we normally do with our integrating factors. I will also just use some basic algebraic manipulations to note that e to the negative ln 1 minus t is equal to 1 over 1 minus t. So e to the t times 1 over 1 minus t is just e to the t over 1 minus t. Just some exponent rules that we're hopefully comfortable with. All right, so I guess I can also just say, yeah, the t turns into that, and then the, 1 minus t turns into that. So now we have our integrating factor. I'll go ahead and multiply both sides of this equation, equation 8, by the integrating factor. And the result is going to be equation 10, that 2e to the minus t equals e to the t over 1 minus t, v prime prime, plus 2 minus t e to the t over 1 minus t squared, v prime. And this entire middle part is going to be equal to e to the t over 1 minus t times v prime of t, and then a derivative of that. So again, this is just always what happens when you use an integrating factor. That's the whole point of integrating factors, is to arrive at this conclusion here, to rewrite it as a derivative of a product. So now we go ahead and just integrate both sides. Integral of the right-hand side is easy. That just gets rid of the derivative. Integral of the left-hand side, which is our new right-hand side, just generates a negative sign. And I will now add the constant of integration. Now, technically, if all you want to do is find a particular solution to the non-homogeneous differential equation that we started with, then you do not need to add this constant of integration C1 that I wrote in here. But I'm going to just choose to write it in there anyways for a reason that will become clear at the end of the problem. So it's optional, but I think you'll be in for a surprise if you can't already tell why I'm putting it there. Now, I still want to solve for v of t. So I'm going to go ahead and just divide by this coefficient, e to the t over 1 minus t. Divide that to isolate my v prime of t and see that it is equal to negative 2 times 1 minus t times e to the negative 2t plus c1 times 1 minus t times e to the negative t. Now I just have to do one more integral to turn my v prime into v. So I go ahead and integrate, left-hand side just turns into v, as was our intent. Here, I didn't show my work for the integration by parts, but this, the antiderivative, will turn into this if you go ahead and do a basic integration by parts. Similarly, the antiderivative of this term will turn out to be this. And then I will again choose to write a constant of integration, C2, because it doesn't have to be the same as the first one, C1. So once again, this is optional. If all you want is a particular solution, you don't have to do this, but I'm going to choose to write this in there anyways. And then we are finally able to conclude that v of t is equal to 1/2 minus t times e to the negative 2t plus c1 times t e to the negative t plus c2. So therefore, y of t, in this case, we're going to get the general solution. Y of t is e to the t times v of t. So if I go ahead and multiply this by e to the t, I get 1/2 minus t times e to the negative t plus a constant c1 times t plus another constant c2 times e to the t. So this is our final answer. And now let's observe. It's actually, there's more to see in this answer. We note that this e to the t, this was a solution to the corresponding homogeneous equation. And we know that because it was given to us at the very beginning of the problem. We were told that e to the t is a solution to the corresponding homogeneous equation. I will let you guys check that t is also a solution to the corresponding homogeneous equation. And you know what? It's so easy. I'll just check it with you right now. If I take two derivatives of t, that's 0, so this term will go away. If I take one derivative of t, it's 1, so this term turns into t. And I subtract from that t, and I get 0. So sure enough, t is also a solution to the corresponding homogeneous equation. And this actually takes some algebra, so I'll just let you guys work it out on your own paper. 1/2 minus t times e to the negative t is a particular solution. It actually solves the non-homogeneous equation that we started with. So what happened with our method of reduction of order is we didn't just get the particular solution, we got the particular solution and the other solution to the corresponding homogeneous equation that was not given to us. And therefore, what we're looking at is the general solution, which is a particular solution plus a constant times one of the complementary solutions plus another constant times the other complementary solution. So we actually managed to get a little bit more than what we originally planned to get, since we decided to keep our constants of integration. So that's all I have to say for this problem. Hopefully you liked it, and if you did, give it a like and subscribe.